Welcome back to the Math Professors. Our YouTube channel covers topics that can be found in any college math class. I'm Professor Van Hamlin, and we're going to do translations on the t-axis and the unit step function for differential equations. So the unit step function, our u of t minus a, is defined by this. It is 0 in between 0 less than or equal to t less than a, and it's going to be equal to 1 for every number a and beyond. So what that looks like graphically is this. This is why they call it the unit step function, is it steps up at a, or we can say that really it turns on a. So we can see that the lights are off all the way till I get to a, and then I turn the lights on for all the numbers beyond a. So it doesn't just have to be dropping from 0 or dropping from 1. I can actually turn off and on any function I want. And let's say something like this. I have this function f of x is equal to 3t plus 1. So it's 3t plus 1 from minus infinity to infinity. But what I want to do is I want to starting at 0, I want the function to be off. So I want it to be off from 0 to 2. And then beyond 2, I want it to be that function beyond 2. So we know this thing piecewise when it comes to like a pre-calculus class. But how do I write this as the unit step function? Well, what I could write this as is f of t is equal to, well, the way we're going to turn this thing on is I'm just going to say it's equal to, instead of being 1, 1 that sits in front of my unit step function, what I'm going to do is I'm going to put this function in front of it. So I'm going to say 3t plus 1, and I want this thing to turn on, so I'm going to multiply it by, the unit function, which is 1, because there's that 1 in front of there, and I'm going to turn it on when t is equal to 2. So this thing will turn on this function at 2. Now, let's do a little more complicated version of some step functions. So, what we're starting at is we're starting at t is equal to 0 for all of these things. So this is only defined for 0 and bigger. So when I graph this thing, what I know is right now, starting at 0, we are the function 4. Until I decide to do something different with it. So it's the function 4 until it runs into this function, which turns on at 3. Now, it's going to start at 4 and it's going to subtract 6 to whatever you have going on. So right now it's going to be 4 all until I get to the number 3. So 1, 2, 3. So it's going to be from 0 to open at 3. Now, at 3, it's now going to subtract 6 to whatever is there. So dropping this thing down 6, 1, 2, 3, 4, 5, 6. It's now going to be at negative 2 from 3 all the way till, it's going to turn this function, this 5 on at 6. So 4, 5, 6. So at 6, it's going to add 5 to this. So it's going to go from here till 6. And now at 6, it's going to add 5 to whatever is here. So up 5, 1, 2, 3, 4, 5. Let's make sure I do this right. So now we're going to be here. Forever. Until I tell it to do something else. Now the reason why these things were horizontal is because the functions in front were just constants. As opposed to right here, the function in front was 3t plus 1. And you can really kind of act like this is, it is the 0 function until I decide to turn 3t plus 1 on at, t is equal to 2. So you can think about it that way, that it really does kind of have a 0 that sits in front. That's why it's 0 in the beginning, as opposed to this one, which is 4 in the beginning. For this example, I want to write this piecewise function in terms of the unit step function. Now, from 0 to a, it's the g function, and everything beyond a, it's going to be the h function. So what we're going to start out with is f of t is going to be, the function that is on from 0 to a. So this is going to be equal to g of t. Now I want it to be h of t everywhere beyond a, but right now it's g of t. And remember, these things accumulate, so in order for me to turn it into just h of t, I have to shut off g of t first. So let's shut off g of t by subtracting it. I'm going to shut it off at a, so u of t minus a. And then I also need to simultaneously turn on our h of t at a as well. Because if I didn't put this in here, it's going to be the whatever the g function is, and then I'm going to add h to whatever that g function was. So I don't want this to be g plus h right here. I want this just to be h of t. So first we start out with g. I have to turn it off so then I can turn on h. So the second translation theorem, where a is bigger than 0, then the Laplace of f of t minus a times that unit step function t of minus a is going to be equal to a to the minus s times the Laplace of f of t. So really this is going to do that translation, so that gives you that e function, and then we're still going to have the Laplace of this function. So, you know, this is gained here and this is gained here. So what this is going to be is, you can see that this is that shift of a of, you know, our capital F of s. So let's find some, let's find the Laplace of, we'll do 3 of them, the first 2 are up. In order to do this, we need these things to have the same arguments, so they have to have the same insides. Now, this one's not a problem because, you know, the functions that live in front of these step functions are just constants, so they have no variables, there's no t in them, as opposed to this one, which does. So these ones are not as bad. That this is, this one's going to be equal to the same thing as 4 times 1 minus 6 times that, let's just pull this out, times the, you know, the unit step function, plus 5 times that unit step function. I know it's a little redundant, but the whole idea of this is, you know, this is 4 times the Laplace of this, so when I want to find the Laplace of this thing, we can pull out that 4, and the Laplace of 1 is going to be 1 over s. I can pull out that minus 6. Now the Laplace of this u function is, you know, it's right here, so I know I'm going to have e to that minus as, where a in this case is going to be 3. But, you know, f of t is just the function 1 again, so I should put a 1 in front of here, boom, a 1, and then even a 1 in front of here. So this is going to be e to the minus 3s times the Laplace of 1, which is going to be 1 over s. And then similar, this is going to be plus 5. This is going to be equal times e to the minus 7s times the Laplace of 1, which is going to be 1 over s as well. So, you know, what we're going to have when we're done finding the Laplace is going to be this. So Laplace with 1 was easy. It just gave us that 1 over s. Now, this, we have a function that's other than 1. But in order for us to do this, they have to have that same input, that this also needs to say t minus 2. So what I'm going to do is I'm going to rewrite this as minus a t minus 2 times the unit step function of t minus 2. Now you can still see that the t is negative and the 2 is positive, so these two things are equivalent. So if I want to find the Laplace of this thing, I should write this as, just to make sure this is the Laplace of f of t for completeness, is going to be equal to that. So if I want to find the Laplace of this side, the Laplace of f of t is going to be equal to the Laplace of this. Okay, so let's start out with this shift right here. That one way we can think about this is that the Laplace of this unit step function is going to be equal to this e to the minus 2s, and I still have, you know, the Laplace of our function, except our function when you just pretend it's 2. So this is going to be the Laplace of just e to the minus t, because I've already taken care of this shift. Now we know the Laplace of e to the minus t is going to be 1 over s minus a minus 1, so it's going to be 1 over s plus 1, so this is going to be equal to e to the minus 2s times 1 over s plus 1, or e to the minus 2s all over s plus 1. Let's do a c that's slightly more interesting. So this one, which comes up a lot in in your diffie-q book, ends up being this, and they want you to pull off the same input, even though we don't see it immediately. So for this to work, we knew that we had to change these inputs to both say t minus 2. For very similar, that t can't be a t. I need this to say t of t minus pi. And there's a little bit that we know about the cosine function, is that, you know, it's it repeats itself every 2 pi because it's periodic of 2 pi. So if I shift it over just pi, what's going to happen is it's going to be upside down. So if I have, like, you know, your cosine function, if I shift this thing over pi, so if I'm looking at it from you know, pi here, and started at pi, instead of this, it's going to be this, it's going to be upside down. So if I shift it over pi and also multiply it by a negative, I'm actually going to get the exact same function back. So that's kind of the claim, is that, you know, 3 cosine of t is actually minus 3 times the cosine of t minus pi. That I'll get the exact same, you know, those are the same functions because of that reason. And then times our u of t minus pi. So it's a cool trick you can do with your trig functions. Hopefully they're asking for minus pi. Actually, if it's minus 2 pi, then you're good. You could just, if this was a minus 2 pi, I could just write t minus 2 pi because it's periodic of 2 pi. Okay, so now that they match, we know if I want to find the Laplace of, you know, f of t, it's going to be equal to the Laplace of this thing. So let's start out with the shift. What I know is that this u function is going to shift this thing over, so this is going to be equal to e to the minus pi s, because of that. And then we're still going to have to do the Laplace of, now we've taken care of that shift, so this is going to be the Laplace of this minus 3 cosine of just t. Remember that once you use this exponential as that shift, this just becomes now the Laplace of this thing without the shift. And we know how to find the Laplace of the cosine of t. We know that it's going to be s over s squared plus 1, because of the 1 in front of there. So this is going to be equal to e to the minus pi s times, well, minus 3. I'm going to put the minus 3 up front. And then the Laplace of the cosine is going to be s all over s squared plus 1. Determine the Laplace inverse using, well, just the inverse of what we just did. So let's find the Laplace inverse of these 3 things. So what we know is that this exponential is, you know, that shift of, you know, a. So let's get started with that. So, and then it's going to also be, you know, times the Laplace inverse of this piece right here. So we know that f of s in this case is going to be this 1 over s plus 2. So that means my f of t is going to be equal to e to the minus 2t. So when we set this thing up, we know that this thing is going to shift the entire expression over by, you know, this you know, shift the expression over right for units. So we're going to have this for the unit function over right 4 units. So this is going to become u of t minus 4. And then similarly, this thing is also going to be shifted by that exact same, argument of the unit tangent function. So this is going to be equal to e to the minus 2 times t minus 4. All right, similarly, we can tell that this thing shifts it, and this is going to be the Laplace function. So we know that f of s is going to be equal to 4 over s squared plus 4, which means f of t is going to be, we can tell that that is the sine function, so this is going to be the sine of 2t. So that means the Laplace of this thing is going to be, well, remember this thing is going to shift it pi to the left now, so this is going to be u of t plus pi. And I'm also going to have to shift this thing with the exact same argument. So it's still f of t, but it's f of t at that particular shift. So this is going to be equal to the sine of 2 times t plus pi. Similarly, we can see that f of s is going to be equal to 1 over s minus 1 here, which I can rewrite this as, I'm going to do the partial fractions for you. You can check these things. Which means f of t is going to be, well, the Laplace inverse of this thing is going to be equal to minus 1, because 1 over s is 1. And then this is going to be plus e to the minus t. So finally, the Laplace of this thing, this is going to give us our unit t minus 2, and then it's going to be this thing evaluated at t minus 2. So this is going to be minus 1 plus e to the minus t minus 2. Now we can distribute this unit step function over to here. So this is minus u of t minus 2 plus e to the minus t minus 2, unit step function of t minus 2. All right, now that we've practiced these things, we just have to put this to practice in our differential equations. So in order to solve this differential equations, we're going to use Laplace transforms. But the first thing I'm going to have to do is I'm going to have to turn this f of t into that unit step function. So we know that we can write f of t as, it's going to start with this t plus 1, and then I have to turn it off when t is equal to 2. So that means I'm going to have to turn this t1 plus 1 off at 2. So there is our unit step function. So that means if I want to solve this, I'm going to have to find the Laplace of both sides. So the Laplace of this left side, so y prime plus 3y equal, well, and then times the Laplace of f of t, which is going to be this t plus 1 minus t plus 1 times the unit step function. Okay, so working with these, we are gonna we know how to do the left hand side. We practiced this enough. This is going to be equal to s times capital F of s minus y of 0, and then plus 3 times the Laplace of capital Y is going to be capital F of s. And now we also know how to find the Laplace of this side, that the Laplace of t plus 1, I don't really need the parentheses there, but the Laplace of t is going to be 1 over s squared. The Laplace of 1 is going to be plus 1 over s. And then we're going to have to find the Laplace of this thing. Now, the problem with this is right now it's not written in terms of the same argument. So in order to do that, we're going to have to we're going to have to rewrite this. Let's have a look at this. So in order to do this t plus 1 times the unit step function of t minus 2, I need this to say t minus 2. So in order to do that, I'm going to introduce a t minus 2, which then in turn is going to have to add 2, and then I still have this plus 1. So what I actually get here is I need to conserve this t minus 2, and then I have a plus 3 times the unit step function of t minus 2. So when I'm actually finding the Laplace of this, I need to find the Laplace of this thing. Now, this now is going to be our function that's been shifted. So minus what we get here, let's take care of this first. We know it's going to be e to the minus 2s. And we know that this is Laplace of t plus 3 times the Laplace of t plus 3. So remember that we're just taking it. We take away the shift because we've already done this. So the Laplace of t is going to be 1 over s squared, and the Laplace of 3 is going to be 3 times 1 over s, or 3 over s. All right, now we know that y of 0 is equal to 0 here. So I can factor out my f of s, and I'm going to get an s plus 3. So combining these two is going to give me a s plus 1. So top and bottom by s, so it is an s plus 1 over s squared, s plus 1 over s squared. And then minus e to the minus 2s, and then combine these two, top and bottom by s is 3s plus 1 all over s squared. So now capital F of s is going to be equal to s plus 1 all over s squared times s plus 3 minus e to the minus 2s times 3s plus 1 all over s squared times s plus 3. Now I'm going to have to do, a system of equations to be able to solve this, and I'm just going to do that now. I'm just going to give you guys the answer to this. So this is going to have to break apart into, this is as squared plus bs. That takes care of that s squared, and then we're going to have our c over s plus 3. And I have to do the exact same thing for this part of it. So, this piece also is going to be some d over s squared plus e over s plus f over s plus 3. And it just so happens that in this case a is going to be a third, so this is 1/3 over s squared, plus b is going to be 2/9 over s. C is going to be equal to minus 1/3 over s plus 3, plus our e to this minus 2s times d is going to be 1/3 over s squared plus 8 over 9 s plus minus 1/3 as well over s plus 3. Now remember that in order to solve for this is capital y sub s, your last step for a differential equation is now to Laplace inverse both sides of this thing. Since I'm out of room, I'm not going to write it twice. So what this is going to be is, your 1/3, and the Laplace of 1 over s squared is going to be equal to t, so this is 1/3 t. Now you're going to have your 2/9 times the Laplace of 1 over s is just going to be 1, so this would be 2/9 times 1, or 1. This is going to be minus 1/3. The Laplace of s plus 3 is e to the minus 3t. And then remember that this is a shift function, so I'm going to say plus, and I'm going to write my shift function u of t minus 2. And this is going to be the Laplace of these things, but instead of writing t's, I have to write t minus 2's. They're going to share the same, argument or input. So this is going to be 1/3. I don't think I give myself enough room. So remember, this would be 1/3, and the Laplace of t squared is just t, but this is going to be t at that shift, so t minus 2. And then this is going to be plus 8/9. Laplace of just s is just going to be 1. So 1 shifted is still just 1. And then minus 1/3. This would be e to the minus 3t, but this is going to be e to the minus 3. Instead of t, we write t minus 2. And that's how you solve differential equations using these unit step functions. So please subscribe. Thank you.